Hi, I'm Bill Kleitz. The material that I'll be covering in this podcast is out of my Digital Electronics 9th edition textbook. I hope you find it useful.
Hi, this is Professor Kleitz. Chapter 16 deals with semiconductor, magnetic, and optical memories. First of all, I'll start out by talking about memory, just general memory concepts, and then we'll compare the two major types of RAMs, the static RAM and the dynamic RAM, and then look into read-only memories. Then we'll look at expansion and address decoding application, which are important in microprocessor-based systems, and then we'll look at magnetic and optical storage. In digital systems, memory circuits provide the means of storing data on a temporary or permanent basis for future recall. The storage medium can be semiconductor ICs, magnetic devices such as magnetic tape or disk, optical storage such as a CD or a DVD. Magnetic and optical memory generally are capable of storing larger quantities of data than semiconductor, but the access time, or the time it takes to locate and then read or write data, is usually more. With magnetic and optical disks, it takes time to physically move the read-write mechanism to the exact location to be written or read from. So in section 16.1, let's talk about just the general concepts of memory. Let's say that you have an application where you must store the digital states of 8 binary switches once every hour for 16 hours. This would require 16 memory locations, right? 16 hours, so for each hour you'd have a memory location. Each location would have a unique 4-bit memory address, 0000 up through 11, which is 0 through 15. So the memory address is going to point to which memory location you want access to. Now, each location is capable of containing up to 8 bits of data as the memory contents. So we've got memory locations having a memory address, and then within each memory location we have the 8 bits of contents. A group of 8 bits is also known as 1 byte. So what we would have is a 16 byte memory, because each location is a byte and there's 16 different locations. So here's what it would look like. So figure 16-1 shows the layout for 16 8-bit locations. So location 0000 is going to have some data in it, 8 bits of data, 1 byte. Location 001 will have some data in it, and so on. We do this 16 times. So in figure 16.2, I'm going to show you how to write data to a 16 byte memory constructed from 16 octal D flip-flops and a 1 of 16 decoder. So the data is going to travel down the data bus to the addressed D flip-flop. First of all, the block diagram looks like this. We've got a 4-bit address that can be 0000 all the way up through 1111. This is going to select the internal contents, and once they're selected, when you pulse the write line by dropping this low momentarily, the information that's on the data bus will travel to the left into the D cells. So basically what we're trying to do is take data that's present on something called the data bus, and we want to load it into this box called the 16 byte memory, and we're specifying the address that the data is going to by specifying the 1s and 0s on the address bus, and then we pulse the write line. So let's look at the actual circuitry that would be used to implement this. Across the top of the diagram we've got the 4-bit address bus, and by the way, these are all coming from a microprocessor or some sort of a digital system, and we're going to set up a 4-bit address. We've got an 8-bit data bus, which is going to contain 1 full byte of data. So basically what you want to do is set up the address you want to write to. Now here's the different D cells. There's D flip-flops. Here's one register here that can contain 8 bits. Here's one here that contain 8 bits, and so on. This one's address is going to be 0000 because when you put 0000 on this address decoder, This output, which is an active low output, is going to go low if you have a write pulse. So this is the deal. What you do is you set up the data that you want to write into the first bank of, or into the first register. So you set up the data, and this data is just sitting here. It's not going anywhere yet until we apply the clock pulse on CP. Then what you do is you set up the address 0000. That sits here. Nothing's going to happen at the output yet until you know you've taken care of the data and you've taken care of the address. Then you pulse the write line. As soon as you do that, these two enables are both satisfied. The address decoder will do its thing, which is to take the 0000 and output a low pulse the same width as the write pulse on this line right here. Now the write pulse, when it goes low to high, that's going to trigger the clock of this D register. This is an octal D flip-flop. So that low to high right here is going to take whatever's on the D lines and stick it into this 8-bit register. Then what you do is you change the data to the new data you want for the second register. So you change this data, and this data, by the way, travels down a data bus. They all get to see it, but only the one you select is the one that's going to receive it. So here's the new data for this register. It's sitting down here. We're going to set up 0001, pulse the write line. The number 1 line goes low high. That's going to trigger this clock, so the data that's on the data bus is going to go into the second 8-bit register, and so on all the way down for all 16 registers. Figure 16.3 shows the timing requirements for writing data to that particular diagram we just looked at, the 16-byte memory circuit from figure 16.2. Now these are the type of diagrams that an engineer or technician will have to look at and understand in order to know how different memory circuits as well as other microprocessor based systems work. When you have a cross like this, what that means is you could have 4 bits of data at this point, and if they're going to change, they're going to change right here. Some of them may be low going high, some of them may be high going low, and they may actually stay the same, but if they're going to change, this is the moment. And same with the data. So with the address bus, here's the old address data information, or the old address information. Here's the old data information. And like I said, you change the address to the new address you want to write to. You change the data for the new data that you want to write to that address. And then after a length of time called TS, which is the setup time, you drop the write line low, and when it goes low to high, that low to high transition has to occur TS nanoseconds after your address and data is present. That's called the setup time. So in other words, make sure the address and data is there before you make the write pulse occur. And then after the write pulse occurs, that applies a clock into the register. It takes a little bit of time called the propagation delay before that new data is going to be present at the outputs of that register. So these are 2 of the time considerations, probably the 2 most important ones that you'll see on data sheets when you look at a memory chip. Okay, so you may have noticed that the cues in this diagram are not connected to anything. What we need to do is take these cues and send them back into the data bus, because whatever data is in these registers, sometime we're going to want to read them. Now the output enables are all grounded. We'll have to remove the ground on these and actually individually select which register we want to dump off to the data bus. So we're going to disconnect these, take the cues and send them back to the data bus. Now to select which individual register is selected, let's look at the next diagram. And figure 16.4 shows us how we can use another decoder to individually select memory locations for the read operations. So we take the same data bus, we're going to set up, let's say we want to look at the first memory location or the first 8-bit register, and we'll put 0000 on these lines, and now we got a new control signal called the read control signal. And by the way, microcontrollers all have a read and they have a write control signal. Usually they are active low. So when you do the read command, we'll get a pulse on this line. When that pulse goes low, that enables this chip, and whatever address you set up on these lines, that output would go low. You take that low and you send it to the not OE enable back in figure 16.2, and we'll send it to the first memory cell register, the next memory register, and so on through all 16 of these. And so using the read command, we can actually access the different 8-bit registers, and when we do that, their information will be sent over to the data bus. By the way, you can't enable all of the registers at the same time because you would have a bus conflict. You'd have some highs and lows that would be conflicting with each other, and one of the chips would burn out. So we have to individually select the different memory cells depending on which address we're placing on the address bus. Okay, so that completes the first section. Next, let's look at some actual static RAM chips and study their data sheets.